students. In this video, I am going to solve questions that were asked in GATE 2024 DA paper from engineering mathematics. So already you would have seen questions from probability and statistics. Now in this video, I am going to solve questions related to linear algebra. So here is the weightage. So linear algebra weightage in GATE DA 2024 exam. So 2 1-mark questions and 4 2-mark questions. So 2 into 4 is 8, 8 plus 2 is 10. So total 10 marks appeared from linear algebra section. Let us solve those questions. So in this, they are asking you, consider a matrix M, which one of the following statements is true. The eigenvalues of M are non-negative and real. The eigenvalues of M are complex conjugate pairs. One eigenvalue of M is positive and real, and the other eigenvalue of M is 0. One eigenvalue of M is non-negative and real, and another eigenvalue of M is negative and real. So to get the answer, what we should do is find the eigenvalues. So if this is a matrix M, how do you find the eigenvalues? If you can find the eigenvalues, you can quickly comment about the answer. So this is a procedure. So we write the characteristic equation, that is determinant of M minus lambda I has to be equal to what? 0. So what is this M minus lambda I? So what is M? M is given as 2 minus 1, 3, 1 minus, so it's lambda 0, 0, lambda. So what is this matrix? It is 2 minus lambda minus 1, 3, 1 minus lambda. Now equate its determinant to 0. So what is its determinant? So it is 2 minus lambda into 1 minus lambda, and then minus of minus is plus, so it's plus 3. This has to be equal to 0. Now you multiply this, you get 2 minus 2 lambda minus lambda plus lambda square plus 3 equal to 0. So it's a quadratic equation in lambda. Solve for the roots. So lambda square and then minus 3 lambda and then plus 5 equal to 0. So if you are okay with factorization, it's okay, but this doesn't fit in factorization, so we'll directly use that minus b plus or minus root of b square minus 4ac by 2a formula. So the lambda value is minus b, that is minus of minus 3 is 3, plus or minus root of minus 3 whole square is 9, 9 minus 4 AC, b square minus 4 AC, so 4 into 5 is 20, and then divided by 2 into 1 is 2. So this is minus root 11, so then we have 3. So by now we got the answer 3 plus or minus root of minus 11 by 2. This can also be written as 3 plus or minus root 11 into I whole divided by 2. So after examining this, clearly the eigenvalues are complex as well as they are conjugate pairs. So do we have any options that way? The eigenvalues of M are complex conjugate pairs. Yes, can you see this? They are complex conjugate pairs. This was a very simple problem. Now they gave a 3 cross 3 matrix M with these entries, and they are asking you the determinant of M square plus 12M. Now what you should not do is, no need to find this M square, no need to check what is 12M, no need to add. So what you are supposed to do is, you are supposed to know the properties of the determinants. According to the properties of determinants, we can write the determinant of, so firstly I am going to use this particular property, let me highlight that. Determinant of AB is determinant of A into determinant of B. So the determinant of M square plus 12M, so how can you simplify this? This can be written as, so if you take M common, so this is M into M plus, so since M is common, so you will have 12I. So now this is what is left. If you carefully observe, this looks like determinant of A into B. So what is determinant of A into B? So it is determinant of the first matrix into the determinant of the second matrix. So it is 12I. So what next? Let us examine what is determinant of M. Okay. So let us observe the elements of M. So here we have 1, 2, 3, 3, 1, 3, 4, 3, 6. If you carefully observe, if you add this and this, what is 1 plus 3? It is 4. 2 plus 1 it is 3, 3 plus 3 6. So what we have observed is, we observed that R3 is equal to, so what is R3? R3 is equal to R1 plus R2. So when you have got this kind of relation, so obviously the determinant of M is 0. So this implies that the determinant of M is 0. Now when the determinant of M is 0, that is if this value is 0, 0 into determinant of 12i, so it doesn't matter what is the value of this, because 0 into any other value is obviously 0. So the answer for this problem is 0, that is determinant of M square plus 12m is 0. So the ones who know the properties can solve the problem in quick, like in few steps. So this was a problem which is asked on subspaces, a very interesting problem, very few would have solved. So let me discuss this. Select all choices that are subspaces of R3. Note R3 denotes set of real numbers. Maybe this is not R3, this is, note this R denotes set of real numbers. R3 is nothing but 3 tuple vectors where each component comes from set of real numbers. So he says you need to choose all such options which form a subspace. So what is this? So he talks about a set which contains vectors such that x is alpha times 1 1 0 plus beta times 1 0 0. That is how A is defined. Now let us look at option B. This x is nothing but again set of vectors which are created as alpha square into 1 2 0 plus beta square into 1 0 1, where alpha beta are real numbers. If you look this, it is a set such that 5x1 plus 2x3 equal to 0, 4x1 minus 2x2 plus 3x3 is also 0, and then option D, it is again a set such that 5x1 plus 2x3 plus 4 equal to 0. So various sets are given to us. We need to identify which of the following is a subspace. Actually, this comes under a MSQ. They have clearly mentioned that it's a MSQ. So it's a MSQ. So let us solve it. Let me minimize this. Here is a question, and this is R, not R3. So how do you solve? Now do you know the rules? So if I give you a set, how do you check whether it is a subspace or not? You need to check all the rules over the vector addition as well as over the scalar multiplication of a vector. Okay, so there are two set of rules. One is related to vector addition, other is related to vector scalar multiplication of a vector. So if you are clear with that, you will definitely answer this question. Suppose, so what do they say? Here they created a set such that it is alpha times this plus beta times this. I will talk about this a little later. Let me first look at alpha square and beta square here. So suppose let me take alpha as 1. So I am talking about option B, students. Let me take alpha as 1. Let me take beta also as 1. So you created a set like this now, which contains, so this is 1, this is 1. So after adding, it is 1 2 0 plus it is 1 0 1. So how much do you get? You get 2, you get again 2, you get 1, you get this vector. If this is a part of the given set, please understand this carefully. If this is a part of this set, then according to the rules of the subspace, now this vector should also be, that is minus x should also be part of this set. Okay, this should also be part of this set, but it happens that minus of 2 2 1 can never be part of this set. You can put whatever values of alpha you want. For example, you can put alpha as minus 1, beta also as minus 1, since there is a square, right? Since there is a square, again what you get is 2 2 1. You will never have a vector of this form in the given set. So according to the rules of the subspace, if x is a vector, then minus x should also be part of this set. Since I have created a vector like this and minus of that is not part of this set, this will not form a subspace. So this option has been eliminated. So this is one such option. Next, if you look at D, I'll try to answer D because I'll tell you why I started eliminating. So this is about B. Now let us talk about D. Option D. So how are the vector, how is this set created? It is created in this way. It is 5x1 plus 2x3 plus 4 equal to 0. So what is x1 now? Or what is 5x1? It is minus 4 minus 2 x3. So let us say let x3 be equal to, let's say, some k, or let's say k1, x2 be equal to k2. Then what is x1? So it is 5x1 equal to minus 4 minus 2, x3 value is k1. So have some patience, see the way I am going to solve this. Minus 4 by 5 minus 2 by 5 k1. So finally how does the solution look? x1, x2, x3. So what are these values? What is x1? It is minus 4 by 5 minus 2 by 5 k1, and x2 is taken as, how much is x2? x2 is assumed to be k2 and x3 is assumed as k1. You can further split this. You can split this as minus 2 by 5, or you can write like this. I would like to take k1 common. If you take k1 common, what is left here is minus 2 by 5 and then 0 and then 1, and then you can also write this as k2. Okay, so if you take k2 common, then this is 0, here it is 1, and again you have 0, and then you will also have another set like this, minus 4 by 5 0 0. This is a very important observation. So why am I doing all this? You substitute whatever values of k1, k2, substitute whatever values of k1, k2. You can never make this solution a zero vector. Okay, you can make, is that clear? So did I say it correctly? I said you can substitute whatever values of k1, k2. Okay, you substitute whatever values. For example, k1 is yeah, I am right actually. You can substitute whatever values of k1, k2. You can never generate a zero solution. You can never generate a zero solution. So maybe you might try. So let me also try. Let's say if you want to cancel this with this, then let's see. I said you can never create a zero solution. Okay, zero solution meaning by x1, x2, x3 can never be 0. So why to verify here? I will directly prove it here. x1, x2, x3 will never satisfy. x1, x2, x3 all 0 will never satisfy this, because 5 into 0 plus 2 into 0 plus 4 will never give you 0. Okay, so meaning by what I want to say is, in this set you will never have a zero vector. You will never have a zero vector. Now why are we stressing on zero vector? Why are we stressing on zero vector? If you want to declare a set of vectors as subspace, zero vector should also be part of this set. Please understand, what did I say? Zero vector should also be part of your set. If zero vector is not part of this given set, then that subset or whatever set they gave can never be a subspace. Now some students might try, and they might try to cancel this with this. Okay, if this is cancelled, then this and this get added and you get a non-zero value. Finally I am saying that whatever values of k1, k2 you substitute, it is up to you. You will never get a solution which is completely 0, like x1 0, x2 0, x3 0. I already proved that, look, you substitute x1, x2, x3, all of them 0 here, this will never form a solution. Meaning by, you will never have a zero vector here. So if you don't have a zero vector, it will not form a subspace. That's the easiest way to eliminate the option. So this is also gone. So don't spend too much time on this. My observation was very, very clear that, look, zero vector, this set doesn't contain a zero vector. Why, sir? You can substitute x1, x2, x3, all of them 0 here. Left side will never be equal to right side. That's enough. Now what are the options that are left over? A and C are left over. It's a MSQ, multiple select question. Okay, so how do you handle this? You need to again check, you need to verify all the properties of subspace. So let's put this here. So let me verify what happens to C and A. Now it happens that in A, whatever x they gave, alpha times this plus beta times this, will definitely satisfy all the properties of subspace. For example, will a 0 vector belong to this set? Let's check. If you take alpha as 0, beta also as 0, so what is that vector you are going to get? You are going to get 0 times this plus 0 times this is a 0 vector. Yes, 0 vector is a part of this. Suppose, let's say alpha is 1, beta is 1, so you get a set 1, you get a vector 1 1 0 plus 1 0 0. How much is this? So this will be 2 1 0. If 2 1 0 is part of given set, then minus of 2 1 0 should also be part of that set. Is that possible? Of course it is possible. Maybe you take alpha as -1, beta also as -1. See what happens? Minus of 1 1 0 plus minus of again 1 0 0. So what you get is -2, -1 and then 0. Yes, if x is a vector in this set, minus x is also a vector in that set. I checked, 0 vector is a part of that. Yes, minus x is also a part of that. Like that, you now check, because these are the important ones. Okay, these are the important ones. I have checked the important rules of the subspace. Yes, it satisfies the properties of subspace without any doubt. A, or the set given in option A, forms a subspace. If you examine this, 5x1 plus 2x3 equal to 0, 4x1 minus 2x2 plus 3x3 equal to 0. So if you solve this, you will get some solutions. That solutions or the set of solutions will also form a subspace. I'll just check few things. If you look at this equation, this equation can be written as Ax equal to 0. You are all good at writing the augmented matrix. So this can be written as Ax equal to 0. So where A is like this, 5, 0, 2, next 4, -2, 3 multiplied with x1, x2, x3. So you are supposed to get a 0 vector. So how much is this? This is 2 cross 3, this is 3 cross 1. So you are supposed to get a 2 cross 1 vector. Yes, so this is a 2 cross 1 vector. So can you convert this into Ax equal to 0? Yes. First of all, will x equal to 0, that is, if I put all zeros here, will that be a solution? Of course, you can check it. In the place of x1, x2, x3, you put zeros. 5 into 0 plus 2 into 0 is 0, 0 plus 0 is 0. 4 into 0 minus 2 into 0 plus 3 into 0 is also 0, meaning by 0 vector is a part of this set. 0 vector is a part of this set. Now what are the other things? Suppose if you find some non-zero solution, let's call that non-zero solution to be V1. So if A into V1 is giving you 0, then A into minus V1 will also give you 0, because this minus is a scalar, you can put that out. Again AV1 is 0. Okay, so what I am trying to say is, again, this is also satisfying all the properties of subspace. Therefore, the answer for this question is A, C. So let's write. So what's the answer? It is A, C. A very beautiful question. You might ask, sir, do I need to spend this much time in the exam? No. So since we want to explain it in a detailed way, in the exam what you should do is, by looking at alpha square, beta square, eliminate. By looking at this plus 4 here, so it is no more a homogeneous thing, it's a non-homogeneous thing. So 0 vector will never be a solution for this, so you can eliminate this. Now this is Ax equal to 0, so no issues. If 0 vector is a solution, V1 is a solution, minus V1 is also a solution, so this do not have any problems. Let's go to the next problem. Which of the following statements is R? Again it's a MSQ. Note, R denotes the set of real numbers. So we need to examine each and every option, a very beautiful question again. So what does the options say? They say there exists M which belongs to R power 3 cross 3, meaning by M is a 3 cross 3 matrix. Here P is a 3 cross 1 vector, Q is a 3 cross 1 vector, such that Mx will give you P has, or such that Mx equal to P has a unique solution and Mx equal to Q has infinite solutions. We need to check whether this statement is true or not. Likewise, there exists M which is a 3 cross 3 matrix, P is a 3 cross 1 vector, Q is a 3 cross 1 vector, such that Mx equal to P has no solutions and Mx equal to Q has infinite solutions. So likewise, different options are given to us. So we will try to verify all these options one by one. We need to analyze each and every option in a detailed way to decide whether it is correct or not. Let's start with option A. Let's start with option A. So what do they say in option A? M is a 3 cross 3 matrix. Okay. So M is a 3 cross 3 matrix. P is a 3 cross 1 vector. That's fine. Q is also a 3 cross 1 vector. And they also say that Mx equal to P has unique solution. So let's write like this: if M into X, Mx equal to P has unique solution. So let's see what happens. If Mx equal to P has unique solution, do you know what are the consequences, or do you know when do we get unique solution? We get unique solution whenever rank of M equal to rank of the augmented matrix MP equal to number of variables. So number of variables. Now when this condition is satisfied, equal to number of variables. Rank of M should be equal to rank of the augmented matrix, and it should be equal to the number of variables. So how many variables are involved here? Since it's a 3 cross 3 matrix, and again on the right side you get 3 cross 1, so X is definitely a, so in this discussion X is a 3 cross 1 unknown vector. So the conclusion is that from this we understand rank of M is for sure equal to rank of MP is equal to what? 3. So this is the conclusion. So one thing, the advantage is we know that rank of M is now P. This is a very important information. So if Mx equal to P has unique solution, what about Mx equal to Q? He says Mx equal to Q has infinite solutions. Is that possible? So let's check Mx equal to Q. If you want infinite solutions for Mx equal to Q, then the rank of M must be equal to the rank of MP, and it should be less than the number of variables, which is 3. But we already said that if Mx equal to P has unique solution, then for sure rank of M is 3. But this is contradicting. Rank of M, it says, must be less than 3. That means option A is a false fellow. This need not be true. So the first option is eliminated. Now let us analyze the remaining options one by one. So let's put this here. So this is done. Let's talk about option B. You need to analyze all these options this way. Okay. So what about option B? Option B, M is a 3 cross 3 matrix, P is a 3 cross 1 vector, Q is also a 3 cross 1 vector, such that Mx equal to Q has no solutions and Mx equal to Q has infinite solutions. Okay, let's see. So once again, what is M? It's a 3 cross 3 matrix. What is P? It's a 3 cross 1 vector. What is Q? It's also a 3 cross 1 vector. They talk about Mx equal to P. That means since M is multiplied with X, so X should be a 3 cross 1 unknown vector. He says such that Mx equal to P has no solutions. Okay, so if, let's say, if Mx equal to P has no solutions, then we can conclude something. So when do you think Mx equal to P has no solutions? Obviously no solutions means rank of M clearly not equal to rank of MP. So this is one of the case. So for example, what is MP? M is a 3 cross 3 matrix, okay, 3 cross 3 matrix which has got 3 rows and 3 columns. What about P? P is a 3 cross 1 vector. So 3 cross 1 vector is like this. So this is your augmented matrix. What is this? This is MP. What is the order? It is 4 cross 4. You might get a situation where rank of M is 3 and rank of MP is 4. See, it's a 4 cross 4 matrix. Is it 4 cross 4 matrix? Oh, is it 4 cross 4? Did I do anything wrong? Yes, I did something wrong. So I did something which is a blunder. So what is M? It's a 3 cross 3 matrix, and then we also clubbed P. So it is a 3 cross 4 matrix, students. So you have to be a little careful. So MP order is 3 cross 4. Okay, you have to be a little careful. So he says no solution. So the no solution can arise here. No solution can arise here. You have to be a little careful. So can this give you a no solution? Let rank of M be 2, rank of MP let be 3. Is it possible? Yes, it is possible. It is possible to create such matrices. Rank of M is 2, rank of MP is 3. That means it has no solution. What next? And he also says that Mx equal to Q has infinite solutions. So Mx equal to Q has infinite solutions. If you want infinite solutions, then the rank of M must be equal to rank of MQ must be less than number of unknowns. First thing is they must be equal, and it should be a value which is less than the number of variables. 3 variables are there, so it has to be less than 3. So can this simultaneously happen? What can simultaneously happen? Can Mx equal to P has no solution and Mx equal to Q have infinite solutions? Yes, it can simultaneously happen, because look at this case, rank of M is 2, rank of MP is 3, no solutions for Mx equal to P. But if you look at Mx equal to Q, you can create matrix such that rank of M is equal to rank of MQ, and you can make that less than 3. So already less than 3 means it can be 2. Yes, this can be a possibility. So yes, such matrices exist. So definitely it's a true statement. Now likewise, you have to examine the other options as well. It is really a very good question. It's a very good question. So maybe let's put this here. So likewise, you need to verify C as well as D. So let us verify C. What is M? He says M is a 2 cross 3 matrix. What is P? P is a 2 cross 1 vector. Q is also a 2 cross 1 vector. Now what about X? Since Mx equal to P, so you are multiplying Mx and you are getting P. So the order of M is 2 cross 3 and P is 2 cross 1. For sure, X order must be 3 cross 1. If you have a doubt, you can check it. So this is 2 cross 3, okay, 2 cross 3 into 3 cross 1, yes. Is it giving you 2 cross 1? Yes. So there is no doubt about this. You can proceed. So what we have concluded is X is a 3 cross 1 unknown vector. Fine. He says in option C that Mx equal to P has unique solution. Okay. So if Mx equal to P has unique solution, let's see what happens. So when do you have a unique solution? When it satisfies this, rank of M equal to rank of MP, okay, rank of M equal to rank of MP, and it should be equal to the number of variables. How many variables are there? So this should satisfy. First of all, what is M? M is a 2 cross 3 matrix. So option C can easily be eliminated without further simplification, because rank of a 2 cross 3 matrix will never be equal to 3. Look at this. It's a 2 cross 3 matrix. The rank of a 2 cross 3 matrix can never be. So what we understand is rank of M can never be equal to 3. That means it's a false statement. Option C is a false statement. You need not analyze it further. This fellow M, which is 2 cross 3, can never have a unique solution. So C is also done. Now let us analyze D. It's a fantastic problem, students. What is M? M is a 3 cross 2 matrix. So they have changed. Earlier it was 2 cross 3, now it is 3 cross 2. Will that matter? Let's see, it might matter because here only 2 variables are involved. In earlier problem 3 variables are involved. So it might change. The approach will change or the answer might change. What is P? It's a 3 cross 1 matrix or a vector. What is Q? It's also a 3 cross 1 vector. Now if you talk about Mx, so obviously when M is multiplied with x and you're getting 3 cross 1, x has to be a 2 cross 1 vector. If you have doubt, you can verify. M into x must give me P. So what is M? It is 3 cross 2 into 2 cross 1 will definitely give me 3 cross 1. Yes, verified. So let's write like this. If Mx equal to P has unique solution, so let's see what happens. So when do you have a unique solution? When rank of M equal to rank of MP, and it has to be equal to number of variables. How many variables are there? 2. So can this happen? Can rank of a 3 cross 2 matrix be 2? Yes. Can rank of MP, so what is MP? First of all, what is M? It is a 3 cross 2 matrix. Okay. Now if you also put P, which is a 3 cross 1 like this, so MP is a 3 cross 3 matrix. Can a 3 cross 3 matrix have rank 2? Yes, you can create such matrices. So yes, it can have a unique solution. Let's say if it has unique solution, then rank of M must be 2. That's fine. Next, Mx equal to Q has no solution, it seems. Okay, so let's see. So if this has a unique solution, then Mx equal to Q has no solution. Acha? So for Mx equal to Q, let's see what happens. So why is he saying like this? There exists. So can we have no solution? Maybe let's check. So for this to have no solution, we want rank of M not equal to rank of MQ. So this is the condition for no solution. So what is rank of M? The rank of M from the this part has been concluded as 2. Now rank of MQ. So what is MQ? MQ is also a 3 cross 3 matrix. You can create Q in such a way that rank of MQ will be 3. Yes, it's possible. You can create augmented matrix MQ. So MQ or MP is already a 3 cross 3 matrix. You can create in them, you can create MQ in such a way that it can be a 3 cross 3 matrix. So in such situations, rank of M is 2, rank of MQ is 3. They are not equal, and that leads to no solution. Yes, such matrix M such that Mx equal to P has unique solution and Mx equal to Q has no solution, such M, P, Q exist. Therefore, it's a true statement. A fantastic question. It will take a lot of time for you to understand all these cases. You need an excellent understanding of basics of linear algebra, especially system of linear equations, to answer this question. I can say that this question is really a very good question. Not only this subspace question was a very high standard question. So out of the 4 questions so far we have solved, this is pretty simple, but this needs good basics. This also needs good basics. Now this is even more interesting. So let's see what is this question about. He says let U be 1, 2, 3, 4, 5 and let sigma 1, sigma 2 up to sigma 5 be the singular values of the matrix M, which is formed by U into U transpose, where U transpose is nothing but transpose of U. So the value of summation I from 1 to 5 sigma I is dash. So they are asking you sum of the singular values of the matrix M. So what to do? So what we will do is, first of all, what is U? U is a Is it a 5 cross 1 vector or a 5 cross 1 matrix? Yes, it's a 5 cross 1 matrix which is non-zero. Yes, it's a non-zero vector. Now, what is rank? What is rank? Many things are involved here. You try to understand it one by one. What is rank of a 5 cross 1 matrix? So, the rank of a 5 cross 1 matrix is always less than or equal to minimum of 1 comma 5. So, minimum of 1 comma 5 is 1. So, what is rank of U? It is either 1 or it is less than 1. Less than 1 means 0. So, the 0 case is not possible because it's a non-zero vector. So, from this we can conclude that rank of U, which is a 5 cross 1 vector, is clearly 1. This is the first conclusion. The rank of the given vector is 1. Now, why do we need this? How is M created? M is U into U transpose. So, what could be the order of M? Can you guess? What is U? It is 5 cross 1 into transpose means 1 cross 5. The result will be 5 cross 5 matrix. It's a 5 cross 5 matrix. No need to find all the entries of that 5 cross 5 matrix. So, what is rank of M? Rank of M is same as rank of U into U transpose. You all know the property that rank of U into U transpose is exactly equal to rank of U. So, which is 1, because rank of U you have said as 1. So, rank of M finally is how much? It is 1. This is one information. So, there are plenty of things that we need to do. So, step by step I will tell you what to do here. First thing is, we have concluded that the rank of this matrix M is 1. Second thing is, if you look at this M, which is given as U into U transpose, let us take transpose again. So, it is U into U transpose whole transpose. So, which is U transpose whole transpose into U transpose, which is U into U transpose, which again is giving you M. That means you got a condition that M transpose is M. We got a condition that M transpose is M. Now, when a matrix satisfies this condition, it means that M is symmetric. What is M? M is symmetric. It's a very important information. It is symmetric and also has rank 1. Now, the property that I am going to tell is applicable for matrices which are symmetric. First of all, what is rank of that symmetric matrix? It is 1. So, if you are having a symmetric matrix of rank R, then exactly there are R eigenvalues which are non-zero. So, remaining all would be 0. So, matrix M has only one eigenvalue which is non-zero, remaining all are zeros. So, let us assume it's a fantastic problem, students. So, since the rank of M which is symmetric is 1, it has got only one non-zero eigenvalue, remaining all are 0. So, let us write like this: lambda 0 0 0 0 be the eigen values of M. So, we already know that 4 are zeros and only 1 is non-zero. Can you find that non-zero eigenvalue? Yes, we can find it. There are many ways. I will tell you how to find it. What you can do is, you add all these eigenvalues, lambda plus 0 plus 0 plus 0 plus 0. This should be equal to trace of M. Trace of M. So, trace of M is same as trace of U into U transpose, which is also same as in this particular case, it is directly the dot product, that is U transpose into U. Sir, how did you know that the trace of M that is created as U into U transpose is directly U transpose into U? So, let me show you an example. Let us take some small example. Let us take U to be something like AB. Let us take U as AB. So, how is M created? U into U transpose, that is AB into AB. You multiply this, what you get is a square and then ab and then an ba, which is again ab, and then b square. Okay, so what is this? This is m. What is trace? Trace of m is a square plus b square, right? Trace of m is a square plus b square, which is same as u transpose into u. So what is u transpose, students? U transpose is ab like this, u is ab like this. Even if you multiply this with this, again you get a square plus b square. So not only for a 2 cross 2, this satisfies for any matrix. Okay, so instead of finding all the entries of m and again taking the sum of all the principal diagonal elements, you better just take u transpose into u. So what is u transpose? And on here the lambda is, lambda plus 0 is same as lambda. U transpose, what is u? U transpose will be like this: 1, 2, 3, 4, 5. This is u transpose. What is u? 1, 2, 3, 4, 5. Okay, so if you multiply, you get 1 square plus 2 square plus so on plus 5 square. So how much this would be? If you find it, I think it would be 55. You please verify. So far we got there is only one non-zero eigenvalue, and that is 55. We have got that. Remaining all are zeros. What next? If m is symmetric with rank 1, so first of all, you please understand, by now you know singular value decomposition. Okay, in that you will learn about singular values. Eigenvalues and singular values are not same, but in some cases, so where m is symmetric, when m is symmetric, your eigenvalues and singular values are very close to each other. They are very much related to each other, meaning by, for a symmetric matrix, your singular values, your non-zero, which are non-negative, the non-negative singular values are same as your eigenvalues. So what I want to say is, first of all, by now you know, since you are attending this course, singular values are different, eigenvalues are different, but in some cases they can be equal. And in this case where m is symmetric, yes, your non-negative, where is that? Yes, your non-negative eigenvalue is exactly your singular value. And you know that since m is rank 1 matrix, there is only one non-zero singular value, which is 55. Remaining all singular values are zeros. Okay, so this particular property is applicable to symmetric matrices. You need to study more about properties of singular value decomposition to understand this. So what I want to say is, right now sigma 1 is 55, sigma 2, sigma 3, sigma 4, sigma 5, they are all zeros. So what is this sum? Summation I from 1 to 5 sigma I. So if you add all this, 55 plus 0 plus 0 plus 0 is obviously 55. Therefore sum of singular values of matrix M is 55. So it's a very not so simple question, very depth question. You need a lot of things here. You need to know the properties of rank, you need to know the properties of singular value decomposition, or you need to know about singular values and their properties. So that's about this question. So I can say that out of 5 questions so far, 2 were relatively easy and 3 were like high standard questions. So people think linear algebra is simple, but here it is the other way. This question is about subspace. It says let R be a set of real numbers, U be a subspace of R power 3, and M belongs to a 3 cross, like R power 3 cross 3, meaning by M is a 3 cross 3 matrix. So be the matrix corresponding to the projection onto the subspace U. Which of the following statements are true? Okay, so here they are talking about projection matrix corresponding to a subspace. So if you have gone through this topic, if U is a subspace, then the projection matrix onto the subspace is given by this. So please try to understand the basics. If U is a subspace, then the projection matrix onto this subspace U is given by, so the projection matrix M is given by A into A transpose into A whole inverse into A transpose. So this is the expression for the projection matrix. Now some people might cancel all this and they might say that it is identity matrix, but before cancelling, A need not be a square matrix. Okay, so you have to be a little careful here. A need not be a square matrix. What some students feel is, they might feel like this, sir, let me simplify this. A into A transpose A whole inverse is same as A inverse and then A transpose whole inverse and then it is A transpose. So they feel like this product is I, this product is I, the whole product is I. No, this is true when A is a square matrix and so on, okay, but A need not be a square matrix. So you have to be extremely careful with this simplification. This need not be I every time. So that's the first thing. Okay, please understand that if you have a subspace U, then the projection matrix corresponding to that subspace U is given by this M, which is A into A transpose A whole inverse into A transpose. By the way, I forgot to tell you what is A. So A is nothing but it is formed by clubbing the bases. So you know U is a subspace. So definitely it has got some basis vector. So you need to combine all those basis vector here. So let's write V1, V2 and so on. So what are V1, V2 so on? They are nothing but the basis of that subspace. Okay. So that's what is A. So now let's not worry about what is A. Let's look at the properties of this projection matrix. So I hope you have understood what is A. A is nothing but the columns of A are nothing but the basis of the subspace. Now let us look at what is M square, because it's a standard property. They're talking about M square, they're talking about M cube. So how do you write M square? M square is nothing but M into M. What is the projection matrix M? It is A transpose A and then whole inverse into A transpose into another M. What is another M? A transpose A whole inverse into A transpose. So anything interesting that you see? Now look at this. This is A transpose A whole inverse. If you treat this whole thing as B, then this is like B inverse. This is B inverse into B. What is B inverse into B? B inverse into B is identity matrix. So if you look at this highlighted portion, this is clearly identity matrix. What is this? This is identity matrix. So what is left? Oh, I did not highlight it properly. Let me highlight it properly. Not about this. You need to highlight this portion. Yeah, this portion. This is like B inverse into B. B inverse into B is always identity matrix. This portion is I. If this is I, then A into I is A. So what is left is something like this, A, and then this portion is left over, A transpose A whole inverse, again A transpose. Interestingly, you calculated M square, you got this, but this is again M, So meaning by what we got is, we tried to find M square that resulted in M square. So M square is same as M. If M square is M, let's see what happens to M cube. M cube can be written as M square into M. Just now we concluded that M square is M. So M square is M, you can substitute that. So M into M. What is M into M? So M cube is M square, which is nothing but M. So that means M power 3 is again M. So this is true. This is also true. Now we need to identify whether A, B are true or not. So you all know the rank plus nullity theorem. So what does rank plus nullity theorem says? Suppose there is something like this, the dimension of the range space of U, okay, the dimension of range space of U plus the dimension of null space of U, okay, dimension of null space of U. This will always be equal to, so for example, so here M is a 3 cross 3 matrix. So this will always, if A is a, let's say, instead of U, let me talk about A. If A is a M cross N matrix, then we write like this, the dimension. This is related to dimension plus rank plus nullity, I mean, so the dimension of the range space of A plus the dimension of null space of A will always be equal to n students, will always be equal to the number of variables students. This will always be equal to n. So in this case, let's talk about option A. If U is one dimensional subspace of R power 3, so I am verifying option A students, very interesting one. If U is a one dimensional subspace of R power 3, that means the range space of U or the dimension of range space of U is 1 plus, then null space of M is one dimensional subspace, so he says the dimension of null space of U is also 1, so 1 plus 1 should give us, so M is a 3 cross 3 matrix, it should be 3. Is it satisfied? No, option A is gone. This is false, this is false. So now let's look at option B. Let's see what option B talks about. I am verifying option B. It says if U is a two dimensional subspace of R power 3, that means if you look at the range space of U, the range, I mean the dimension of range space of U, it is 2 plus, if you look at the dimension of null space of U, it is given as 1. Is it equal to 3? Yes, it is equal to 3. Yes, 8 is a true statement. It is a true statement. Which one? Oh, I am sorry. Option B is a true statement without any doubt. So it's a MSQ and the correct answers are B, C, D. A fantastic problem once again on subspaces. This completes the solutions to linear algebra. So this completes solutions to linear algebra. So I can say one of the best questions you have got in DA paper from linear algebra. Thanks for watching this video.